Hello, my name is Nitin. Spiag has finally released DAISY 8 for 6 module R&D, which is advertised to offer more flexibility for customized measurements with Spiag and third-party probes than any DAISY system before. It has been designed for non-standardized measurements typically required by R&D groups. Today, I will perform a first simple test by evaluating the distributions of electric field, magnetic field, and field impedance inside this transverse electromagnetic cell to determine the extent of the field volume with a well-defined plane wave characteristics. I feed the TEM cell with a signal generator and an amplifier. The power flowing through the TEM cell is monitored by a power sensor connected to this end through an attenuator. The measurements will be made at 250 MHz using the EF3 dV probe first and then the H3 dV probe measuring the same volumetric grid. Now that the hardware is ready, let us move to the software and set up the measurements. I run the DAISY 6 module R&D and make sure that the correct probe and data acquisition electronics are selected in the hardware setup. Next, I start the module R&D Jupyter Notebook. The notebook has a display with the preferences, setup, and measurement tabs. To fix a reference frame for the measurement setup, I first define a phantom in the preferences tab and rename it to TEM cell. The phantom is defined by a single point, which is taught to the system by moving the robot tip inside the TEM cell to the center of the septum. The home position is defined by moving the robot to a position outside the TEM cell. The home position is a safe point, easily accessible by the system without any possibility for collision. Next, we move to the Setup tab and define a communication system as continuous wave CW at 250 MHz in the communication systems table. It is possible to define custom communication systems by entering duty cycle, peak to average ratio, bandwidth, and period values in this table. To set up the measurement sequence, I add the move to home and setup phantom commands to the table. For the setup phantom command, I ensure that the correct phantom TEM cell is selected. Next, I add the commands volumetric scan to the measurement sequence and edit the properties to the correct values for the volume inside the TEM cell. I also select the export file name for measured values. I can preview the scans to make sure I have the correct settings. Module R&D offers several additional options to define scans such as the circular scan, point cloud scan, roll scan, etc. and provides a simple graphical user interface to run complicated measurements with a few button clicks. As I am now ready to execute the E-field measurement, I move to the Measurements tab and run the complete sequence in one go. As the robot moves and measures, the GUI updates the job status for each individual job. The measurements are also shown graphically. After the E-field measurements are completed, I change the probe to H3DV in the physical setup as well as in the hardware setup window. I also perform the probe alignment to make sure that the center of each measurement point is identical to that of the E-field measurement. Next, I copy the volumetric scan from E-field measurements in the measurement table and reset it. I select the export file name for H-field values. I also add the post-process EH scan field command for calculation of impedance values from the electric and magnetic field measurements. Now, I run the H-field measurements and accelerate the video. The measurements are now finished and we can look at the results using the Visualize button. The E-field distributions as individual field components or total field can be visualized as interpolated field using surface, contour or heat maps in the XY, YZ or XZ planes. To calculate and display the field impedance plot, I click the post-process EH scan field command and set the correct files for E and H field export from previous measurements. Now, I run the command. This command calculated the field impedance at each measured point as the ratio of E and H field values. The impedance plot shows 377 plus minus 10 ohms in a relatively large volume of almost 40 into 40 into 40 millimeters in the center of the TEM cell that I can use as my calibration volume. The fields are poorly defined close to the opening as expected. The procedure is indeed easy and straightforward. The new DAISY 8 or 6 module R&D is a definite plus from SPIAG, and especially for people like me who use the system for much more than standardized compliance testing. So, for example, for custom development or special measurement tasks, DAISY 8 is a great platform. It has many diverse applications: WPT, TAR, HAC, millimeter wave, and now with the module R&D, any custom defined applications are also possible. This means that my system is always busy and utilized, and the return on investment is quicker. The DAISY 8 or 6 module R&D graphic user interface is simple and easy to use and already provides quite a few scan options. SPIAG promise to include import of custom phantoms and test setups in the next version. I'm already looking forward to the next releases. Thanks for watching this video.